Good. So today, the webinar, we're going to discuss about radioactivity in the environment. And I've picked a couple of subjects to discuss. The presentation takes about 45 minutes. And after that, we have a small question and answer session, about 15 minutes. If you still have some questions left or the question is too broad to be answered quickly, you can always email me or send the question to the email address that we will publish at the end of the webinar. I would like to ask everyone to turn the microphones off so we don't have any feedback. But if you have a question, just write your question in the chat or put it at the end of the presentation. But before I will start, I would like to tell a little history, a little bit a story of a hero. My grandfather-in-law, François Vauvy, was captain of a crew of an Halifax heavy bomber plane in the Second World War. And he flew from York, Elvington to Germany to damage their infrastructure. And on one of these trips, he did about 40 trips, he was shot down. And being clever and smart, he let the motor run. And that meant that the gunner could operate the machine gun, and that saved the crew. And for that, he got the highest medal from France, and hence he became an officer of the Legion d'Honneur. So yeah, a whole story of a hero. What has this to do with radioactivity? And the answer is on the left-hand side of the screen. You see there the inside of the cockpit. And all these dials and numbers and hands and things had to light up in the dark because they were also flying at night. And to do so, they used radium paint. And that lights up, that glows in the dark. But before we go into and dive into this radium and radioactivity business, let's refresh ourselves what actually is radioactivity. Often people ask me, can you measure the radioactivity? And then I said, yes, I can, but what type of radioactivity you're interested in? And if you look at radioactivity, what is radioactivity? Actually, it's the nucleus of an element, of an atom, that has an imbalance of protons and neutrons, and it seeks to balance itself. And one way it can do is it's performing an alpha decay. What it does, very effective, it takes 2 neutrons and 2 protons and throws that out of the nucleus, like that. That's alpha decay. There's, however, another way that a nucleus can get rid of the excess of neutrons or an excess of protons, depends how you look at it, is by taking a neutron, convert that into a proton, and throw out a beta particle or an electron, which we can picture like that. Then, of course, we have gamma emissions and gamma rays, and everyone always thinks about gamma rays. Oh, well, we can see skeletons. So there we have a picture of skeletons. But what is a gamma ray? What is actually gamma emission? Gamma emission is the release of additional energy that a nucleus still has after following one of these decays, an alpha decay or a beta decay. I sometimes compare this, and everyone with children will recognize this, is a child needs to go to bed. It needs to go to its rest state. And before going to bed, it's going to run around. He or she needs to get rid of the extra energy. And that's a little bit also what the nucleus is doing. And it sends a gamma ray out. These are the three major decay modes that we will encounter. There are a couple of more. One of those is a positron emission. Positron emission is very special. A positron is basically the other side of the electron. The electron is negative. A positron is positive loaded. It's antimatter. So what it does, it throws out this positron, and the positron reacts with matter, and it becomes energy, which we can detect. It also can choose to take an electron from its nearby electron shells, combine it with a proton, make it a neutron, and in that way trying to balance the neutrons and protons. A little bit like that, and that leaves a gap in the electron shells, and that's filled up again, and this whole process causes some energy to be released as X-rays. A very disastrous way a nucleus can get rid of the excess is just to split into two, a spontaneous fission, which looks like that. So that is a little bit about radioactivity. And radioactivity is using a special unit. It's called becquerel. And a becquerel is basically the atoms that disintegrate or fall apart per second. Now, this unit does not necessarily tells you how much radiation dose you receive. Radiation dose has to do with how much harm the radiation particle, an alpha particle or beta particle, does in your body. So there is a conversion factor applied to the level of becquerels and the type of radiation to the radiation dose you receive. And that is expressed in sieverts, or more convenient in millisieverts. And living on Earth, on the average, gives you about 3 millisieverts of radiation dose. Now, let's go back to radium. What is radium? Radium is an element that is discovered by Marie Curie in 1902. And it's a natural element. It's just everywhere in nature. And it's formed by the decay of uranium. Radium, the name radium, comes from the fact that it was radiated, and it was radiated blue light. And apparently, at that time, radium was emitting this blue radiation. It's in fact not exactly true. What happens is that the alpha particle excites the nitrogen in the air, and then it falls back to its ground state by emitting its additional energy as that we see as blue light. Radium was used in this luminescence paint, like in clocks and instrumentations, in combination with a phosphor component. And this phosphor compound was reacting with the alpha particles. The alpha particles excited that phosphor compound to a higher energy state, and then it fall back to its ground state, and then we could see it was glowing green. So it was not actually the radium that was glowing green, it was the combination with the phosphor components. And over time, due to this alpha bombardment on these phosphor components, they were deteriorating, and over time they were not glowing anymore. But that didn't mean that the radium wasn't there anymore. The radium is still there. And very early on already, and you can see here a picture of a journal in 1915, they knew already that radium could cause cancers, mainly oral cancers, so cancers in your mouth were described. And the reason for that was that to get a very pointy brush, the people that were painting us were putting the brush in their mouth and just make it sharp, but by that also getting some paint and hence radium in their body. Now that radium paint was used till about 1960, and now a lot of these airfields and factories are abandoned, and people would like to repurpose those, for example, for housing estates or something like that. And before they can repurpose this, there needs to be a risk assessment done about the radiation risk of the radium there. It might be polluted, then there need to be a cleanup. And to do that, we go to the fields and set up a couple of radiation monitors on tripods. Now, the picture you see here is not an airfield. I cannot show you a picture of an airfield because of the confidentiality that is associated with the work that we do. So I show you here a mud field. We do exactly the same measurements to measure the distribution of radiation and normal environmental radiation. So it looks really the same. This is just not an airfield. So on these tripods, there you can see this kind of stacks here as well. And those are the radiation monitors. And we map the radiation fields over that site. And we get the picture where the hotspots are. Where is potential contamination? And we go back to it. We take a handheld monitor like that. And you can see there that it reads some counts per second, alpha and beta radiation. And we pinpoint where potential contamination is. We take a sample in pots like that, and we send it to my laboratory to further test on that. Now, how does such a radium test look like? Radium is an alpha emitter, but it also emits some gamma rays. And that are these gamma rays that we're going to use in a detector, or to detect the radium, I have to say. And we have a room with a couple of detectors there, 6 detectors in total, and you cannot really see the detectors. The detectors are in these kind of gray cabinets, and these cabinets, we call them lead castles. They're cabinets made out of lead shielding. It's not that the radiation is so dangerous that we need to shield ourselves from this radiation. The shielding is there because the detectors are so sensitive. And would we not have these cabinets around, we would measure the radiation, the natural radiation in this room, in this brick wall, in the ceiling, etc. So that's why we place them into these cabinets. And we put on a robot, and the reason is that we have just a higher throughput of samples. A typical measurement is about 5 hours. We collect the radioactive or radio decay events during 5 hours, and working 24 hours a day, which a robot can do, we can analyze around 200 samples a week. So that is important. And in the video that I'll show you now, the detector just has calibrated, the robot just calibrated this detector. And it's now going to see if the place, the designated place where the calibration source should be, is empty. That is very important because we need to know where our source is. The source should not be in a place where it can do harm. I was now going to see if the source is indeed on the detector, and it's going to pick it up. There it is. And it brings it back to the space where it should be. It then going to do a double check. It asks itself basically, did I really pick up the calibration source from the detector? Is the detector free and available for a measurement? It's going to do that first. Check, is it empty? Yes, it is. And then it needs to bring the sample to the detector. But before it does that, it needs to have also a place when it can bring the sample when it has been measured. So it's first going to check, is there an empty space on the table where I can put my sample when it's measured? And it is empty, and then it's going to look for the sample. It checks if the sample is there. And there it's going to carefully pick up the sample and bring it to the detector. It's going to place it on the detector. And then it's going to close this lid. So it sits in a completely closed cabinet. And it's not doing that by its hand. It's just sending a comment to this small control box. And there we see the detector has been closed. And my measurement commences. And then hence we can measure radium. There are a little bit some issues with measuring radium in this way. And the major problem is that uranium, also naturally present, is interfering with this measurement. Now, normally, this is not a really great of a problem. There's a minor overestimation. Now, there are ways we can work around that. We can, for example, look into our gamma spectrum. Can we find other gamma lines from uranium-235? And sometimes we can, but sometimes these lines are so fake, so minor, that we cannot really use that. Another way we can do is assume that the radium is natural, but that is of no use if we're looking for a contamination. There is another way. We can look at another nuclide that represents radium in a way. And to understand that, we need to look at the decay of radium. So if radium decays with a half-life of about 1600 years, after 1600 years, half of the activity is left, it emits an alpha particle and some gammas, and then it becomes or decays into radon. And this radon is a gas and it's radioactive. So it decays as well with a half-life of about 4 days. And then that decays to polonium. Everyone knows polonium because a Russian spy was assassinated by that. And the polonium has a very short half-life, decays to lead-214. And the lead-214 is the one that we are interested in, because the lead-214 is a beta emitter, but also emits some gammas. And if we wait long enough, then this becomes, we call that a secular equilibrium. Basically what happens is that the number of atoms of lead-214 that decays away are formed again. And then this activity equals the radium-226 activity. And we get, as we call that as an analytical chemist, an unbiased estimate for our radium. The radium activity is then correctly measured. But here there is a problem. Once we take the sample and we put it in a pot and it goes on a truck and it comes in a laboratory, then we need to dry it and sieve it and mill it and prepare it. And all these things we do with it causes the radon to escape from the soil. Now, if this radon is gone, the polonium is not formed anymore, but it's still decaying. And in 3 minutes, there's half left. So in 30 minutes, 1,000th is left. So basically, it's then gone after 30 minutes. And for our lead-214, that's within 5 hours. So not of any use if we do it in our pot. There is a way though, if we put it in a pot and that pot is airtight, then the radon is forming in that pot and stays in the pot, and the lead-214 will be formed. But it takes 25 days to reach again this secular equilibrium where the lead-214 is an unbiased estimator for our radium-226. And sometimes we do need that. Sometimes we need to wait this long, and especially when we seek in our project compliance with ISO 18589. But often that initial measurement that might be slightly overestimated is often good enough to see, do we have here a contamination or not? And then, of course, we come with the next question. When do we consider the soil to be radioactive? Because you can see here, the soil naturally is radioactive. We have potassium in the soil, and on the average, that is 380 becquerels per kilogram. We have naturally uranium 238 and another type of uranium 235 in the soil. And these decay, and there's a lot of other nuclides there associated with that uranium, and altogether gives that a 420 becquerel per kilogram of that specific uranium 238, or 15 becquerel per kilogram for that uranium 235. Also for thorium. Thorium is also there, so 384 becquerel per kilogram. And if we look specifically at radium 226, average natural levels are around 30 becquerel per kilogram, although in some areas, like in Cornwall, this might be much higher. So we might do our measurements and we can say, oh, the soil is radioactive. The law takes that into account, and in a good guidance document, it explains the law and explains that if your soil is contaminated with 1,000 becquerel per kilogram radium-226 that is used as paint, then it is not classed as being radioactive. If it's over this 1,000 becquerel per kilogram, then it is radioactive and you need to do something with it. You take it off-site, for example. Now, you are allowed by law to take into account this background level, but you need to demonstrate that that is your background. So you just cannot pluck a number out of the air. So one way of doing that is saying, okay, I have here my site. I go just outside of the perimeter, or I go to a parking lot or a known space where a parking lot was, where we know there was no radium contamination. We take a sample and then we measure that sample, and we can deduce not only by looking at the radium, but looking at a lot of other indicators indicating radionuclides. Yes, this is the natural radioactivity level for radium on this site. And we can use that and we can subtract that to lower that initial measurement and see if our activity is below this 1000 becquerel per kilogram. However, we also need to take into account other radioactive contamination on that site. It might be, for example, that there was a firing range on that site and they might have used depleted uranium. Then also you need to take that into account. And this number might be lower. Now, we as SOCOTEC can give you some guidance on that, but if you need legal advice, you really need to discuss this with a radiation protection advisor, or so-called RPA. So that about radium. So my next topic I want to discuss is radon, another natural radionuclide. We have seen radon already a little bit. And on my right-hand side of the screen, we see a map of the United Kingdom. And the more brown it is, the more radon is measured there. And if you want to know how much radon is in your area, you can look this up. It's an interactive map. You can type in your postcode and you can see how much radon is there in your area. And the problem with radon is it's a gas, and it's an alpha emitter, so it can cause lung cancer. And about 1,000 people or 1,100 people, quoting the government there, in the UK die of the inhalation of this excess of radon gas that has accumulated in people's home or workplaces. And the problem is a little bit with the radon is that you cannot see it. It's colorless. It doesn't glow green or blue or something. You cannot smell it. You cannot see it. You cannot taste it. But you do inhale it. So we can monitor for radon in the workplace or your home. And then we can do some remedial measures. For example, we install extra ventilation. And then after that, we of course need to measure again, because we need to know how effective these measures are. With radon, there is another problem, because radon also kind of dissolves, in brackets, into the groundwater and also potential drinking water sources or bottled water sources. So spa water is very healthy, but it should not contain too much of the radon. And we offer a lot of measurements to make sure that your water source complies with this radon concentration and with other radioactivity that might be in the water. And the UK has implemented the European guidelines on that. Now, how do we test radon? As I said, it's very difficult. Radon is gas. So if you take a sample and you transport it, the radon most likely goes out of that water. So you need to have a special bottle, which we provide. And this bottle is airtight. Now, if you fill this bottle, you really have to make sure that there is absolutely no air in this bottle. If there's a little bit of air, like a small air bubble, the radon gas goes into that air bubble and the measurement is invalidated. You don't measure the radon anymore because it's in the air. And once we open the bottle, it goes out. When we're going to measure, we do a test in accordance or compliant with ISO 13164. But we ask you to send this bottle back within 1 week. If you look at the ISO standard, it says within 24 hours. However, we did some tests here, what the effect was on storage and transport, and we feel that 1 week is still okay to do a measurement. You can see also on your right-hand side the decay of radon, and you see that the half-life is about 4 days. So after 4 days, you have half of your activity left, and after 1 week, you have a quarter left. So you see also why, therefore, this week is important. Because otherwise, the radon has decayed away so much that we cannot detect it anymore. To detect radon, we use a technique called liquid scintillation counting. And these are the instruments that we use for it. There's not much to see about it because the detector is hidden inside this box. And it has to be in this box because it has to be done in the dark. And the reason for that is, if we go to my next slide, is how the test works. We take very careful from the middle of your bottle 10 milliliter of your sample. And we do that in duplicate because we really absolutely want to be sure that the taking of the test portion was done correct, and we should end up with 2 exactly the same results. On top of that, we do an organic layer, it's kind of an oil, and the radon will be trapped by this oil. And in this oil, there is a so-called scintillant, a little bit similar as how that phosphor compound worked in the paint. The alpha particles and also beta particles, because you can see radon decays, and we have 1, 2, 3 alpha particles and 2 beta particles, are reacting with this molecule called the scintillant. It gets in an excited state, falls back to its ground state by emitting its additional energy, which we can see as a purple light. So the detector I showed you on the previous slide is actually not measuring the radioactivity. It's really measuring the light, and the light intensity, or the intensity of the pulses of light after each interaction of these radiation particles, is a measure for the radioactivity present, or radon present. And the result is a kind of graph like this, in which we can classify the energy of these alpha particles and beta particles, so we can see what it is. And here we see the first alpha particle from radon. And the next one, it decays to polonium, has an energy very close to this first alpha particle. So we can just see it. There it is, a very small spike. It then becomes lead-214. We met that one before as well. It was so handy to measure the radium. And the problem with beta particles is that a beta particle does not give us such a nice spiky signal. It kind of gives us a dome like this. Here's one, and here's another one, and here is one that goes in the alpha particle. So we can detect that too. And there we see those, this one and this one, are from the lead-214. That then further decays to bismuth-214, and bismuth-214 is a much harder or more energetic beta particle which sits over here. So this graph is basically kind of a sorting station and sorts the energy, the measured energy of the particles, and hence we can see what it is. So there we are. We measure our radon, and we can compare the activity with the stated threshold value in this European guideline. And as I said, the UK has just implemented it. And the radon concentration should be less than 100 becquerel per liter. There are also, there are other radionuclides that you need to measure for to make sure that the drinking water is indeed drinkable in terms of radioactivity. Of course, there are other tests they do on it, but this webinar is on radioactivity. And the other thing that you need to measure is tritium. And tritium you can see, kind of see as radioactive water, and that should be less than 100 becquerel as well. And then you need to demonstrate that the radiation dose that someone receives by drinking this water should be less than 0.1 millisieverts per year. Now, we said already that you need to convert these becquerels into millisieverts by applying conversion factors, and to approach that and to demonstrate that. So these radon and tritium are separate items. Is you can approach it by performing a gross alpha or a gross beta activity measurement. We don't know exactly what it is, but we measure the alpha radiation flux and the beta radiation flux from that sample by basically evaporating all the water, collecting the salt, and measuring the flux from that salt. And to hit that 0.1 millisievert per year, or not to hit that 1.1 millisievert per year, better saying, is your gross alpha activity should be less than 0.1 becquerel per liter, and your gross beta activity should be less than 1 becquerel per liter. And if one of these tests are failing, you need to do other tests, which we can provide as well, of course. And you can look into alpha spectrometry or gamma spectrometry to see what is it that causes this to exceed these numbers. Now, how do we measure the gross alpha activity? I said already, we collect the salt from your sample and we measure the alpha flux. But how can we convert this flux into a becquerel? Well, we need to assume something because we don't know what it is. But we know that the range of alpha particles, and we just have seen an example of that, is huge. And we can say, well, we assume it's natural radioactivity that is most likely to be in our water. So what will be the average energy of an average alpha particle? And we can calculate that. And then we say, oh, in our range of calibration sources, we have americium 2-for-1. And americium 2-for-1 happens to have an alpha particle energy that is equivalent to that average energy of this natural radioactivity. So it's really useful to use this as a calibration. It doesn't mean that americium 2-for-1 is in your water sample, not at all. It's just the nuclide that we have used to convert this flux of alpha particles into a becquerel per liter. And of course, the same can we do for the beta flux. And then it happens to be that the natural potassium-40 is actually also a very good estimator to convert that flux into an activity level. So that is how we convert those fluxes. Now, looking at that, there is also, of course, artificial radioactivity in the environment, not only natural one, because we are using nuclear power plants to provide energy. And on the right-hand side, you can see all the nuclear installations of the UK. And SOCOTEC is providing the government with a lot of measurements to monitor the environment for these artificial radionuclides, making sure that that natural environment is safe. And we measure a lot. So instead of the radiation flux that we measure with these tripods, we can also change that detector into a dose rate meter, and we measure the dose rate across the United Kingdom. But we do more. We also take samples and measure the contamination of plutonium, americium, uranium, but also carbon-14. And we're not doing carbon-14 because we want to know how old the soil is. No, carbon-14 and also tritium is released by the nuclear power stations. Also, gamma emitters like cobalt-60 and radiocesium, like cesium-137 and cesium-134, are monitored for, as is radiostrontium or strontium-90, technetium-99, and sulfur-35. And there is, behind all of these nuclides, there is a reason why we monitor them. And I'm not dwelling into that. What I really would like to do is to show you what the impact of this, of these discharges are on the radiation dose that you receive. And this is all published in a RIFE report. And you can see here a pie chart of the exposure and what the source of the exposure is. And on the average, this adds up to 3 millisieverts per year. And this small purple line represents the nuclear power production or the energy production from nuclear power plants. And actually, that contributes to your radiation dose per year of 0.01%. It is even lower than the 0.2% that the nuclear weapon fallout still contributes to your radiation dose. Now, we discussed already radon, and you can see that radon is a very important factor in your yearly radiation dose, about 48%. You get a little bit of radiation from going to the dentist, and then the dentist takes an X-ray to see if your teeth are still healthy. Living on Earth gives also a little bit of your radiation dose, and the sun shines as well nicely, and that gives you also a contribution to your radiation dose that you receive every year. And by eating food, you also receive some radiation. Because, as I said already, potassium naturally is radioactive, and by that you get an intake of some radionuclides, and that contributes to your overall radiation dose. Now let's have a look at some of the nuclides that are discharged, authorized, discharged into the environment, and how they behave in the environment. And first of all, here we have a small map. Sellafield there, Lake District, nice walk you can do. And the radiation that is discharged here is transported this way along the coast. And then it makes a big loop that way. And here we have a very nice mudplane. This is not, I don't think this is the photo of that mudplane. Sorry, I couldn't find one. But we look the same, mudplane here, and we measure the radiation and we take samples. And one of the nuclides that we measure in this mudplane is plutonium. And here we plot those plutonium concentrations as becquerel per kilogram dry sediment in the years, over the years. And here we see that there is an authorized discharge from Sellafield, plutonium, but the plutonium here in this area is still going down. And only after 3 to 5 years, we see a small peak appearing. And actually it's 5 years, and you can see 1993, and then the peak appears here in 1998. And then it goes down a little bit. Oh, sorry, I have to go back, go too quick. We see again a authorized discharge here in 2003, and 5 years later, we see it appearing in our mud plain. And we also see it starts to build up. So it kind of accumulates there. So it takes 5 years to go from here to here, and then it settles there. There's a little bit, nowadays there's not much discharge anymore. There's some, but not big loads anymore. And what we see is that slowly the plutonium concentration is going down. It's quite conservative, as we call that. And of course it's decaying as well, but the half-life is so long that we don't see that here. You might see that in 100 years. So it stays there. Now, looking at another nuclide, cobalt-60, we see a completely different environmental behavior. First of all, again, we see that authorized discharge, but now it arrives in about 3 years at that mud plain and settles down. But then it also disappears quite quickly again. It's quite mobile. It is also decaying, but the half-life of cobalt-60 is 5 years. So this peak of 70 becquerel per kilogram, would it stay there and not being so mobile? After 5 years, we would see a number around 35. So we are around 2000. So we are then at 2005, and we see a slow decrease. And we don't see that. We see a quick decrease. It means that it is dispersed into that environment, either by bio uptake of animals, or it's washed out, leached out. Because we see here a second discharge, and again 3 years later we see that, and then we see a very quick release. And we see a little discharge there, and again kind of a shoulder there, and then it goes down, and then that goes down further. So here we probably see a combination of decay of cobalt-60 and washing out. And that brings me to the end of my presentation. I hope you enjoyed the presentation, and if there are any questions that I can answer now, let me know in the chat, and otherwise send your question to webinars.uk@socotec.com, and then I'll get that question and I can answer that in more detail. Are there any questions? People have their hands up. No. Not at the moment. Well then, I thank you all for your attention. And if you have still another question, just please let me know. And yeah, enjoy the rest of your day. Thank you very much.